Hello and welcome to my second video on 3D graphics for the Nintendo 3DS. So in this video I will go over how to draw textured cubes, planes and 3D sprites from float arrays and indices arrays, which is different than what we was doing previously in the last video, which you kind of need to have watched to get what's going on in this one. Then I will go over how to correctly draw 3D sprites and billboards. If you recall from the last video, they were not sorted correctly and the depth of them all appeared wrong. And they were also distorting objects in the background as well. And then thirdly, I will show how we can mix 2D and 3D on the top screen, with 3D being drawn first, and then we switch to a different shader to draw our 2D screen. And we use the method from the previous video with drawing things in immediate mode to achieve that. So first off, let's have a look at the demo so you can know what I'm talking about here. So we've also added back in the 2D from the 2D videos. So the top screen here relies on assets that we load in, whereas the bottom screen here relies on 16-bit or 8-bit raw pixel data in arrays. So everything on the top screen here is loaded from assets. And then you'll see here we appear to have like two different fonts at the top here, and then we have a motorbug and a bat sprite and a fish sprite as well. That's using the virtual 2D layer. And then we can move around our scene here in 3D. We have the 3D sprites, which are the flies, which are correctly ordered. You can move around with the various controls, and then if you press the left or right button you will increase the amount of flies buzzing around. So if I move around here you can see every time we press left or right, a random fly appears and then buzzes around the scene there. So you can make up to 100 flies. So that's what we are generating. So first off, let's carry on with this. So quick refreshers here, everything's generated with shaders on the 3DS. So our 3D graphics goes through the vertex shader, a fragment shader, which is all contained in the one shader before going to the screen or the monitor. This is the sort of OpenGL style here, whereas as I've gone over in the previous video, the 3DS versions of all of this uses this shader code here, which is ARM code. This is the shader for the 2D graphics, and all it takes in is it takes in a projection matrix and a model view matrix, and then it takes in just the position of our vertex and the texture coordinates, and then just multiplies them with the model view matrix, projection matrix, and then outputs the pixels here at the end. And then all 3D models or meshes are made of polygons here. The 3D space, as in the same for sort of OpenGL, negative Z goes into the background, positive comes out through the monitor towards you, positive X goes to the right, negative X goes to the left, positive Y goes up, and negative Y goes down. And then your rotations, obviously it's hard to picture these from here alone. Then our draw order is always counterclockwise, although I think you can actually change this on the 3DS, but I'll be sticking with counterclockwise as everything else uses it other than DirectX. And then when we construct our models, we always construct them in local space, and then they are then scaled and translated to the global space or the level or world space. Missed off a G there. So drawing 3D models. So in the last video I showed you how to draw them in immediate mode, and the reason for that was to quickly introduce you to drawing 3D in a simple fashion. So in this video we will be generating our models from arrays of floats and unsigned shorts or U16s for creating our indices lists. So I'll quickly jump back and forwards between the slides and here to try and make things make sense. I think this is it here. So we will need to flip between some of this here. So we have this data structure here which holds our textured vertex stuff. So we have 3 floats for each vertex's position, 2 floats for the texture coordinate, and 3 for the normal coordinate. So you can, as per everything else, these are pretty much just each dot here is a vertex, except rather than just describing the position, we are obviously describing the texture coordinate and the normal coordinate. I'll assume you've watched the previous videos, which I've kind of explained what these are, so I will not be doing that in this one here. So we have a few mesh shapes here. We have a floor plane, and then I have a value here which allows you to scale the texture for the floor. So if you have a texture value greater than 1, then that basically means that the texture is scaled, so it basically repeats if you set it up to repeat, which is a nice quick way to enable more detail. So if I change that back to 1 and we rebuild this, and then if we rerun this, and then try and move around, let's have a look around. So you can look at the floor here, like, and then I'll scale this up. Don't really need to scale this, to be honest, as the texture we're using is actually quite high. yeah, you can see there the there's loads of them in there now, like. But yeah, as you can see, we've the detail has been lost by scaling this up. It only makes sense if you've got like a low resolution textures, really. As the 3DS can pretty much handle massive textures, there isn't really any need for that there. And then we have our array for our sprite, which is basically, it's the same as a plane, except you can think of it as being like rotated instead. And then here we have our indices list. So what this basically describes here is what order each of these dots or vertex should be drawn. So as we are drawing triangles, there are basically 3 verts per polygon, hence the 6 verts needed for each of the planes. And then we have 2 different types of cube. So the wall cube has its origin not in the center, it's actually at the bottom. I think it's the bottom left, which is nice and easy for when you sort of like, if you're creating a level, you don't have to sort of move the mesh to the center location on the position where you intend it to be. That probably doesn't make any sense to you, but well, when you sort of start playing around with levels. And the other thing to note here as well is this uses just one face for each face of the cube. Sorry, it uses the whole texture, whereas this other cube uses a sub-region. So if I jump into the graphics here, in fact, did I implement that? So this demo is basically a copy of the one I've released recently for the Nintendo 64. And on that one we were able to change the wall texture by pressing a button. So let's add that back in. In fact, no, they're mixed, so we don't need to do that. Did I rebuild this? Let's double check. Okay, as the mixed, that's fine. So you'll see the these are the wall cubes here. And then if I look around, let's try and find the button for it. Here you go. Here's the other cubes here. So you'll see that there's a sub-region allocated for each face. And what that is doing there is just open this up in an image editor a minute. What that's doing there is it's dividing the image into 3 vertically. So as per the previous video, all images are normally they're converted to floats and normalized. So the size is always 0 to 1 height wise and 0 to 1 width wise. So the origin of text coordinates is usually at the bottom left, 0, 0. And then the top right would be 1, 1. So to draw that region there, or that sub tile in this image, it would be 0 to 0.5 or 0.49 width wise. Might have to adjust that to make sure that the text coordinate was actually within this region and not starting to encroach on the other tile. And then height wise, that would be 0 to like 1/3 of the height, so 0.33, or probably slightly smaller than that, again to make sure that the graphics doesn't bleed onto the other texture part. So one thing to note as well is this image is stretched height wise, and the reason for that is because the 3ds only likes its textures and images to be like powers of 2. So if the original size here was 32 by, I think it was 48, as each of these are or were 16 by 16 pixels in size. But if you put the original image in, internally it gets resized anyway. So I ended up with the pixel area from 48 to 64 being transparent, which obviously caused part of the cubes to not be drawn. So there's a bit of info for you there, like. And then one thing to note as well is the sprite sheet here. So when you're working with the 2D side of things, you obviously need to load an image in with all of your graphics. So because we are working with the immediate mode 3D, we can provide them with each region of the tiles in here. So if you only wanted to do like a 2D sort of style game, you could just use the 2D stuff in here, not the 3D. Load in all of your assets on the top screen and then do it that way. So the on here, the top screen is actually a 32-bit screen, and then the bottom screen is a 16-bit with a 1-bit alpha. If we didn't do that, so my Ring Dash game, which I made for the 3DS, it uses like the shader I use for the top, it uses for the bottom screen and the top screen, but each of the sprites on it are actually 3D mesh, and I found that I wasn't actually able to draw everything in one go. There was if you try and draw too much 3D on the 3DS, the emulator just crashes. I'm not sure whether the real thing just tanks like that, but if you try and draw too much, then the emulator will just tank. So I kind of had to split the drawing of the bottom screen, which was a bit of a pain, whereas this way, having the bottom screen use the frame buffer method of drawing seems to be a lot better. And then obviously both of the screens can kind of be totally independent to one another. So back to the 3D models here. Talk. So basically we supply our vertex data, which describes our mesh or model, and then we use that to draw the whole shapes. So first off, we have to describe the parts of our mesh, and then we have to create buffers to contain this data here, so we can readily draw these here. So I have this structure here which holds everything here. So basically to draw a model using buffers, which is the main way that you'll kind of be doing this in any proper sort of scene or game, we basically kind of need various bits and pieces to be able to draw these. So this is kind of I've kind of deduced the things needed to do this from the various examples for the 3DS, and trying to understand the various bits needed here. So what we have in here is we have two dynamic arrays that we need to allocate, and then we need to know how many verts and indices we have. So one vertex is basically a position, a text coordinate, and a normal. So this is 1 here. And then you'll see here I have the vertex count recorded for these, and the indices count as well. So the indices basically, as I said, they describe which order to connect these vertex together to form the mesh. As each of these, so each face of the cube basically takes 6 of these indices here, which reference 6 of these vertex here to create a plane. So we need those numbers to describe how to build the model, and also for how to later draw it. And then this here is the main sort of buffer object in here from Citro 3D. So to create our mesh, first we need to initialize the mesh manager here. So you see here I have a fixed array of these meshes here, these mesh data buffers. So if you want to have more than 10, just increase that number there. So note that there's only 4 mesh that we are actually using in this demo here. Obviously if you had a game, then you would have a lot more in there potentially. So each new sort of mesh you added, just increase this number here so that the list of these is increased. It's easier just to use an array at the start here rather than playing around allocating more of these. Just makes it a bit simpler. And then to add a new mesh, you literally just pass the array for the vertices, the vertex count, the indices array, which would be that one there, and the indices count. And then behind the scenes, what it then does is it picks an unused mesh data object from our mesh list. It then passes the passed in parts, the indices count and the vertex count, and then in here we initialize the buffer info object. Not quite sure what actually goes on there, because if you have a look in here, which is the header provided, there is no description what actually happens. So this is kind of like a black box to us. And then we say how many bytes each data type, which is a T-vert or a textured vert, which is this here. So basically how many bytes one of these structures actually takes up. That also describes how to go from one vert to the next. We then pass in the vert count and the indices count to this. We then work out the total mesh size, so that would be the item size times the vert count. This is another weird data type which has to be provided. So this kind of describes the order that the data is passed in. So it's kind of in reverse order here. So 0 on here indicates the position, 1 indicates the texture coordinate, and 2 indicates the normal coordinates. And this describes in reverse order where each of the data parts for the vertex to be drawn can be found. And then we pass in how many attribute types. So that's 3, as we have position, text coordinate and normal. And then we start allocating the size of our data buffers in here. So I've named this VBO data. If you've played around with modern OpenGL, you'll be familiar with the vertex buffer objects. Basically, it's just an array of floats. This array here will basically store all of the graphics data from one of these. It'll all be copied across and put in here for us to repeatedly draw whenever we wish. So we allocate the size of that array to basically encompass all of our vertex. Then we allocate another array to contain all of the indices. So basically make an array same size as this, except in bytes. So that would be 72 bytes in size basically. And then if all that was successful, then return true. So at this stage here, we've basically allocated a blank container to copy all of our data in here, and then that's exactly what happens next. We cast the vertex buffer object into a textured vert data type, one of these, and then we can literally just iterate over all of the verts, just copying them straight across. Except one weird thing you have to be aware of here is the vertical texture coordinates. They are flipped the wrong way around, so we have to correct that. So the way to do that is to basically reverse them. So normally they're from 0 to 1, so if we do 1 minus that texture coordinate, then that will turn it the right way up. So that basically copies all of the vertex to the VBO, and then we do the same thing here with the indices. And then if that was all fine, we just increment internally the mesh count. And then to draw one of these mesh, you just pass in the ID number from the array here. So one thing I recommend you do is create a header file with a list of mesh. So you see here I have floor, wall, cube and sprite. And then if we jump into the main function here, where I initialize all of these, you'll see the order here matches the order here. So just keep a reference of what order you add all of the mesh in, and then it's as simple as that. To draw them, you literally just call s3d draw model with an s3d data type. Let's jump in here. So the s3d model data type contains a position, scale, rotation, a texture ID and a mesh ID. The mesh ID obviously will be one of these. You then fill out these for where you want and how big you want a model to be, and then call draw model, and then internally what that does is bear with me here. So you see at the end here we call the draw method here for the mesh, but beforehand we create a model view matrix. We work out the correct rotations by converting them from degrees to radian, and then we copy the camera's model view matrix, or rather the camera's view matrix, into the model view matrix. We then translate the model view matrix by the position of our model. We then rotate it we then scale it. We add in the light, bind the texture, and then we set the relevant shader parts up. So we pass the projection matrix from the camera, then the model view matrix to the shader, which is the 3D shader for it. And then when we call the model mesh draw function, this then uses the shader program to draw the various triangles. So you see here, to draw this, we first have to call C3D set buffer info. Then we create a pointer to our indices buffer, and then we can call the C3D draw elements function using triangles, and then we pass the indices count. The unshined short data type is the data type for the indices, and then we pass the index buffer object in, and then this uses the buffer info data, I guess, to point the shader to the correct parts to draw with, and that is what we will be doing in all the future videos. This here will not change. All of this here will not change. So this is the main way that, according to the, or rather using the 3ds demos, it appears to be the way to go. Like, there is also in the 3D thing here, there is also some immediate mode stuff as well, but the that's reserved now for just drawing the 2D stuff on the top screen. So that's the mesh manager stuff there. Hopefully that makes sense to you. If not, then just use it as a way to get your stuff drawn until you are happy with what's actually going on there. So let's jump back in here. So we've covered how to draw 3D models there using the mesh data buffer object. So now let's quickly go over the billboards from this slide here. So the billboards is, or sprites, sorry, are all of those flies. So if we have a look in here, what's actually happening, we have an array of these flies here. So each of these are 3D sprites. So if I bring up the S3D header again here, you'll see this is the various parts our sprites take. So this is pretty much the same sort of stuff as from the last video where we were drawing them. The only difference in this one here is we, with the draw sprite thing here, where are we here? This basically works out the position and the rotation of the sprites here and scales them internally. and then it pretty much does exactly the same as the 3D model one here. The only difference is we point, or rather we rotate every sprite towards the camera. So to do that, we use a function called getAngle2D. So you can use this for tracking as well. Basically what this function does is it works out the angle between two groups of coordinates in 2D. So we pass in a source X and Y, and then the target. And then what that does is it uses the atan2 function here. We times that value from radians to degrees because it returns the angle in radians. So we convert it to degrees and then we return that value. And then that will tell us the difference in angle between 2 points. So you could use it for like simple tracking, where you have like a target position or a target object that you want something to track, and then you pass in the source's coordinates, and then it tells you what angle you need to rotate that model towards for it to follow it. So all we do here is we basically get the yaw angle of the camera. We set the sprite's Z rotation to that. No, sorry, we set the sprite's Y rotation to that before using the mesh manager to draw the sprite. So that's how we draw the sprites now. So notice that there's no change in we're not disabling like backface culling or anything here, which is why you make sure that the sprites are actually pointing at the camera. If they rotate the other way, then they will be invisible, as we don't need to do any we don't need to disable culling in this version here. But one thing we do need to do is to sort them by their distance from the camera to draw them. So one of the things that we have to do to work with 3D sprites or billboards. So for example, if you think of like in certain games you'll have like grass and various other sort of scenery all around the place. Those are 3D sprites or billboards. And for them to correctly allow the transparency to work, you have to sort them in distance order. So what you do is you draw the furthest one away from the camera first, and you draw the closest to the camera last. So if you imagine all of these rotated squares here are billboards we wish to draw. The eye here represents our camera. So if we were to sort them by distance, one thing to note as well is we want to get rid of the sign value. So that means whether it's like a positive or a negative number. We're not interested in the positive or negative aspect, purely the absolute value. So going by this here, you would see that 3 is the furthest from the camera here. So that would be the first one to draw. And then we would have 4 next, then 5, then 1, then 2. This would be our list which we would construct based on the distance away from the camera. Then once all of the normal solid 3D objects have been drawn, you then draw the billboards afterwards. That also goes for any models which have transparent parts as well. You would, if you had like say a car with like translucent windows, or a window which had like a transparency to it, these things would have to be added to the draw sorted distance list as well. That's because the when these things are drawn, the hardware has no way of knowing that parts of them are actually transparent. That's only sort of the Z buffer, which is what's responsible for drawing polygons at a distance. It doesn't know about the transparent pixels, so you need to help it by sorting the correct distance that these things should be arranged in. Hopefully that makes sense to you there. So in here we have a list of fly objects. So you have a maximum here of 100. This info here is just to set some sizes and some boundaries for our little scene. This part here is the sorting function. It uses a bubble sort to do that. We have basically one loop inside of another, and then all we are doing is we are comparing the distances between one fly and the next. We're using pointers to do this, so you'll see the outer loop is using the J index, and the inner loop is using the I index. So we're basically iterating over the loop twice. So what happens here is everything is internally sorted by iterating over it twice, basically. What happens is we use pointers here. If the distance of one object is less than the other, we create a temporary pointer. We then copy one object to that pointer, and then we basically switch these two objects over, and that ends up creating the correct draw order to use. So when we come to the render function here, all of the flies will be correctly sorted for us as we work on this list directly. The add function basically just creates a new fly. So there's nothing too special going on here. We draw all of the floors here. So we only basically use one model here. We don't need to store too much of the details. So in this first part here, we basically set all of the parameters of the model to be one floor object, and then using the width and height of our world here, so you could easily sort of change that, make that bigger there if you wanted. Now if you have a look around here, see everything is a lot bigger. So you can fly up and down, and then look left and right using the A and B buttons, I believe. I've kind of tried to create a decent setup for the controls as if it was like a first-person shooter. I've also added in using the C sticks as well on the new 3DS and 2DS, should you have those. And then this part here just draws the wall blocks here. So the floor is basically 3 times the size of a tile, which is why they're going in steps of 3 here. So this one here is the size of a tile, and then these here are basically the size of the level in tiles. If you basically think of a 3D scene as in like a 2D scene, it helps to kind of imagine things being constructed in tiles. The sizes are obviously up to you to decide. And then the second part here, this draws the rotating models here, where it just gets like a random position basically based on the sizes we set out above here. Nothing too magical here. Like the key thing in here is how simple it is to actually draw these. That's the key point to all of the stuff here, is to make things as easy as possible. So one thing, so we've gone over the billboard stuff and the drawing 3D models. The next part is the 2D setup. So there's nothing too magical in here to talk about. Some of this stuff is from the 2D videos, so any of that I don't really need to sort of go over again. The only thing to note here with the Scene 2D stuff is in here now, this version of it only works on the bottom screen. I could not get the top screen to work using frame buffers, unfortunately, which is why I had to fall back on having to use a 2D shader and a 2D render list, which I will talk about shortly as well. So let's jump back into here now. So to use our 3D, first we have to call s3d begin, and the reason for that is we now have to split up the process of drawing stuff between using the 3D shader and the 2D shader. So if I come up into the beginning here now, so in our shaders list we have 2 shaders now. We have our 2D shader and our 3D shader. So we first set up the 3D shader here, and then we set up our 2D shader below. So this also illustrates how easy it is to add more shaders using the shader structure I created here. Again, you just need to describe what's actually in the shader, which I talked about at the beginning. Let's have a look. We'll side by side this so I can describe it properly. So you'll see here we have two uniforms, the projection matrix and the model view matrix. And that's these here. This is how you pass stuff in. So any matrix that you pass in, they're basically these fvec array functions. You basically convert a matrix into an array of these fvecs. That's basically a float structure, or a vertex 4 if you like structure. So it's basically a 4x4 matrix comprised of 4 of these fvecs, and then we describe the parts we're passing in here. So we're only passing in a position and a UV. So if I copy those and put this down here, and then you'll see here the inputs we pass here: position and a text coordinate. So that's our two shaders set up there, and then you will see in here, where is it? We have to set up another projection matrix for it. Let's have a look. Yeah, here we go. Here's our orthographic projection matrix for our 2D scene. So we have another projection matrix for drawing our 2D, which is defined. Where is it? There we go. So we set up our 2D projection matrix here. And as we are creating the 2D layer for the top screen in here, we kind of have to duplicate some of the 2D functions. So you'll see here we have a print center, add font, and tile put. So all of these here I would use rather than these ones here. So these will immediately draw these things, whereas these here, they add the draw commands to what I call render list. So what that is basically on any modern console. So you think here I have done this on the DS as well when I've not used sprites. For example, if I was, sometimes there's no point using hardware sprites on the DS. You can literally get away with using bitmap sprites, which is kind of what we will be doing on the 3DS, as there is no way to sort of do any sort of hardware sort of drawing of sprites or anything like that. So the easiest thing to do is to create a scene object. So the sheet ID basically refers to the image ID, or in our case the texture ID. I'll explain this more in a moment. And then we have the tile ID to draw. So if I get back to here a moment, so back in the main function here, once we've initialized stuff, we obviously have to load in the various graphics and create the meshes. So the texture manager now, it has functions to create like tiles internally. So we have a way to kind of split stuff up. So we have one like normal way to load textures, and then we have this other way where we load textures and then we assign tiles to them. Let me explain that a bit better here. So inside the textures now, we have a rect list. This is basically a handler for creating arrays of rectangles for us. I'm sure I sort of covered some of this in the last video, possibly. I'm not sure if I did this in the 2D one or not. Anyway, what this allows us to do is create like lists of sub graphics inside larger ones. So if we come back to we have a sprite sheet in here, or an image sheet, whatever you want to call them. They're basically the same sort of thing. So you see in here, this is our image here, or texture, and then we have some different areas in here. So we need to create references to where each of these sub images lie within our texture. So again, the texture is always from 0 to 1 width and 0 to 1 height. So you kind of have to divide that up. So you have to kind of try and record the rectangles for each of the tiles, which is why they have the rect lists in them, and whether they have tiles in them or not. So if they do have tiles, then you need to add those in, as in the numbers. So you can assign tiles by basically passing in where the pixels are, and then internally the tile functions will convert those into the correct UV positions. So there's only one image sheet in here. So when you load in the texture, you obviously have to pass in the width and height. As you'll see here, this is 256 by 128. And then you have to say whether it's sprites. The reason for that is it needs to know whether there's going to be any transparency used or not. So if you are having transparent parts in there, then pass true in there. And then once you've done that, you can then create tiles using that textures ID. So again, in here we have a list of texture image sheets, and then these are like tile sheets in here. Although I don't think these are actually used. And then these are just some numbers which refer to the sizes of things in here. Some of the important ones here, the texture tiles here, this refers to the tile IDs, as all of the tiles are added in here. So when you pass in some tiles, you need to pass in the image ID, which would be the texture ID. So I think internally, let's have a look, there's a, yeah, it's keeping two lists in here. So we have the normal textures and the image textures. So the image textures would just be anything like this which has sprite sheets in, or tile sheets, sorry, either or. So as these are all using the same image, you need to record where they all start inside. So first we add the 12 by 12 pixel font, then the bats and fish, then multibug is added, and then the final font set is added. So it's always best to keep references to where all these things are, which is what the these defines are doing here. Then once you've done all this, you then need to add the fonts using Scene 3D. So you need to know where the ASCII start is. So that is normally the first ASCII ID number of the character. So 32, which is the one I usually start with, is the space character in the ASCII character set. You then pass in the size of each letter, how many letters are in that font set, and then the tile ID where that font set starts. Similar to the S2D function. And you'll see we add in the second font there as well. So any fonts you want to add in, that's how you do that. And then so you'll see we have in the title run here, before we draw any 3D, we have to call S3D begin. That where are we? That will then attach the 3D shader and set up the various culling and texture environment variables, and then update the 3D camera as well. Then you can draw the 3D parts, which in this demo is this one here. So it's draw floor, but it actually draws the walls as well. Then update the fly's positions. So that moves them all, and then it sorts them by their distance from the camera, then it draws the flies. These are just dealing with moving the camera. And then the next part is call S3D 2D begin, and then you can draw the various 2D parts to the top screen. And then another thing to note as well is once you've finished drawing all of the 2D stuff, so all this is doing, so you could kind of this doesn't all need to be after this actually. So this could be kind of anywhere, because all what's actually happening here when you call all of this is these images are basically all of the details here. This is just working out the parts of the tile to put into the into a scene object, and then that's added to the render list for drawing at a later stage, which is what you must do with these two things here. The 2D begin part basically binds the 2D shader and sets up the 2D projection matrix, and then the draw 2D batch that just in fact that's already in here anyway, so we could probably just we could just fucking get rid of that. So with that gone, what this does then is it just iterates over all of the objects which are now inside this render list, and then it calls the ZS3D draw 2D tile part, which is this here basically. So you kind of have two options with drawing the 2D stuff. You can do everything with the batches here, or you could just call the where are we? Or you could just call S3D 2D begin and then use the tile 2D put function anytime after that, and then this will just so if we I'll demonstrate this a minute here. So this one here kind of does things immediately, whereas this batches stuff up in the render list. So let's have a look. But no, we better not use that. So you see here we have to pass in the image sheet ID and then the tile ID to use. What did I call these? Text tile. So let's, okay, this will look a bit jarring, but this will demonstrate the immediate drawing stuff here. So that's the bat being drawn at random locations there. So you can either use the batch list method of drawing tiles and everything, or you can draw things immediately. So another thing to note there as well is there's another function here as well. So you can actually draw an image directly here. So what you can do with this one is if you were not drawing the 3D stuff, you could use this to draw like a title screen. So what this will do is this will draw the whole sheet. So you see here, this is drawing that whole image sheet over the top of the 3D scene here. I suppose you could use it for like creating like a rain effect or snow or something like that, I suppose. Like, so this draws like a whole image, and then this draws like a tile from an image, but without it being batched. So if you're not going to do any of these, then you need to call s3d 2d begin, and then you see we don't have any of the text printed out here, but we still have the 2D stuff being drawn. It's just being drawn immediately rather than stored in a list for later drawing. So that's two options for you there when it comes to doing the 2D to the top screen. So I don't think there's anything else I want to cover in this. I think everything's there. So one thing to be aware of is you can draw the 2D first and then draw the 3D. However, what happens is I haven't been able to find a way to kind of correctly get them to work together. So weirdly, what happens is there's kind of the 2D thing here, so it turns off the culling and the depth test, but it appears that if you change that during the whole process of drawing, so if, for example, you drew an image as the background and then switched to S3D 3D begin, drew your 3D scene, and then tried to draw 2D on top of that again, all of the 3D like models and parts, they would all be turned inside out, as I found out trying that in Holodash version for the 3DS. So the takeaway is if you were doing like a title screen or something, just have the 2D begin part, draw your title screen, as long as there's no 3D on your title screen. That's fine. However, mixing 3D and 2D, always do the 3D first and then the 2D after all of the 3D. That's my suggestion there. And again, if you draw loads of stuff and then suddenly everything just doesn't work anymore, then that's because you're trying to draw too much 3D. It's hard to judge how powerful the 3DS actually is, to be honest. I tried to do everything from the Wii version of my game Horror Dash onto here, and it literally tanked, which I was surprised. I thought the 3DS would probably be kind of equally as good drawing, but that wasn't the case. So just something to look out for there. So I don't think there's anything else I need to cover here. Obviously, everything needs to be freed before you exit. And always call the mesh manager init function before you start adding meshes. And S2D and S3D init need to be called, or rather the S2D init needs to be called before you obviously add in the textures as well for that. So that's it for this video. In the next video, we can build upon all of this, and instead of passing in vertex arrays and indices arrays like this, we'll be using the same format that I use on the 2DS to convert OBJ models into signed and unsigned shorts. So we'll be able to load models from arrays. In the next video, I'll go over using more interesting models rather than textured cubes. This is just to introduce you to using the mesh data object, the mesh data buffer, just to get you familiar with the various parts in here. So if you have any questions, let me know in the comments below, and if it's anything related to my code, I'll probably be able to answer it. If it's anything to do with some of the DevKit Pro data types, then maybe I'll be able to answer it. Depends whether any of it's commented or not. So that's it for this video, and I will catch you in the next one. Thanks for watching.